You are listening to Sales Optex. Visit us at salesoptex.com.
So, picture this scenario for a second.
Okay.
You're an executive or a division manager or honestly just a professional who is trying to keep your head above water in a really, really rapidly shifting industry.
Right, which is pretty much everyone right now.
Exactly. So you're sitting at your desk, you open up your morning industry newsletter, and boom, there it is. Your primary competitor has just signed this massive partnership with a highly hyped artificial intelligence startup.
Oh, yeah. That is exactly when the panic sets in.
It really does. And we're not talking about, a modest tool for sorting your spam folder. We are talking about a firm that claims to specialize in strong or general artificial intelligence.
The kind of tech that promises to essentially act as a digital superbrain for your whole company.
Right. Optimizing every single facet of the business. So your heart rate spikes, the imposter syndrome flares up, and the fear of missing out it's overwhelming.
It's a very specific, modern kind of professional anxiety. I mean, we see it everywhere.
We really do. So naturally, you go into research mode. You pull up this startup's website, and it is an absolute masterpiece of modern tech marketing.
Oh, I can picture it now.
You know the one. You are greeted by these high-resolution video headers of young, incredibly trendy people. They are sitting in an exposed brick WeWork space, drinking artisanal cold brew. And there is almost certainly a golden retriever sleeping under a standing desk somewhere.
Of course, and the glass whiteboard in the background.
Yes, the glass whiteboard that is completely covered in these impenetrable, chaotic mathematical formulas. And the copy on the website borders on pure science fiction. They don't just promise a software update, right? They promise a total paradigm shift.
But the friction happens when you try to actually connect those lofty promises to your day-to-day operations. You look at the slick marketing, you read all the buzzwords, and you realize there is absolutely no obvious overlap between what the startup is claiming to do and the specific, messy, complicated reality of your own supply chain.
Or your sales pipeline, or your customer service queue. But the pressure is relentless.
Yeah, it is.
You are looking at the landscape, and you're thinking about your next quarterly review or that upcoming board meeting. And the temptation is just to cave to the fear. The instinct is to scramble, find another AI provider with an equally slick website, write a seven-figure check, and just cobble something together.
Just so you can walk into that boardroom and say, don't worry, guys, we have AI too.
Exactly. So today, we are asking you to put the pen down and just take a breath. We are going to step back and look at this landscape objectively. Whether you are prepping for a high-stakes strategy meeting where you have to defend an IT budget, or you are simply a curious learner trying to understand how this machinery actually operates behind the curtain, you are in the right place.
The mission for this deep dive is to cure what we are calling AI fever. We are going to cut through the exposed brick, the buzzwords, and the science fiction. We are going to break down exactly when a business should actually use machine learning, which we'll just refer to as ML, and equally importantly, when you should run in the exact opposite direction.
And after we establish those boundaries, we are going to explore how the top-tier engineers actually build real, profitable working systems without, just burning through millions in venture capital.
Which is the most important part.
It is. And we have an incredibly rich stack of sources guiding our conversation today. First, we are looking at a highly pragmatic white paper from Bain & Company, literally titled The Cure for AI Fever. It is just an essential guide for separating business reality from technological hype.
It's a great piece. And second, we are pulling from a document that is treated basically like scripture in Silicon Valley. It's called Rules of Machine Learning, Best Practices for ML Engineering.
Yeah, written by Martin Zinkovich.
Right, a research scientist at Google.
Okay.
It is the ultimate insider playbook for how the biggest players actually build these systems.
And to balance that out, we have a very grounded breakdown from Quimatics, a company that specializes in AI software for sales. They provide this brilliant, hard-nosed look at four specific situations where you absolutely must not use machine learning.
And finally, to really test these concepts at the absolute bleeding edge of global scale, we're unpacking an academic presentation from Daniel King at Lancaster University.
Yeah, his work is fascinating. It focuses on applying machine learning to massive, complex, next-generation telecommunications networks, specifically things like software-defined networking and network functions virtualization.
So we have corporate strategy, Google engineering rules, pragmatic business warnings, and cutting-edge academic network design.
It is a massive amount of ground to cover. Okay, let's unpack this. Because to understand why AI fever is infecting every boardroom in the world, we have to define what machine learning actually is and how it differs from everything that came before it.
Right, we essentially have to completely flip how we think about what computers actually do. The Lancaster University presentation offers a remarkably elegant way to understand this paradigm shift. It all comes down to where the complexity lives.
Okay, let's start with traditional programming first, just to set the baseline.
Sure, so for the last 50 years, the complexity of a computing system lived entirely within the code. Human beings had to sit down, understand a problem perfectly, and write a highly specific step-by-step program to solve it. In that model, you feed the computer two things: the raw data and the program.
Right.
The computer runs the data through your program, and it generates an output.
So to use a really basic analogy, traditional programming is basically like baking a cake. The data represents your raw ingredients, the flour, the sugar, the eggs. The program is the recipe. The exact instructions to mix for 5 minutes and bake at 350 degrees.
Exactly, and the output is the finished cake.
But for this to work, the human programmer had to know exactly how to bake a cake. They had to understand the chemical reactions, the exact measurements, every single step.
And that is the bottleneck of traditional computing. It relies entirely on human comprehension. If we don't know the steps, we can't write the program. Machine learning completely flips that equation. In machine learning, the learning algorithms themselves are actually quite simple in principle. The complexity, the deep, hidden structure, is no longer in the code the human writes. The complexity is in the data itself. So instead of feeding the computer the data and the program, you feed the computer the raw data and the desired output.
And the computer's job is to figure out the program.
Right. It has to find the hidden pattern.
Okay, so going back to the kitchen, this means you give the computer the raw flour, the sugar, the eggs, and you show it a photograph of the perfect finished cake. And you tell the computer, look, I don't know how to make this, but figure out the recipe.
That's exactly it. The machine then tries a million different combinations, failing over and over again until it discovers the mathematical relationship that turns those specific ingredients into that specific cake.
But what does that flip actually mean for a business? Because it sounds like it changes the entire corporate structure of an IT department.
It absolutely does, and this is a profound business implication that executives often miss entirely. In the old paradigm, your most valuable employees were the logic architects, the software engineers, who could write incredibly complex, perfectly structured code.
Right.
In the machine learning paradigm, you no longer need people to write the rules. You need data engineers. You need people who know how to source, clean, and organize the ingredients. The algorithm itself is often an open source tool you can just download for free. The competitive advantage is entirely in the quality of your data.
So the technology is acting as a function approximator. We use these systems specifically when human beings cannot mathematically pin down the functional relationships ourselves.
Think about calculating the sales tax on an online shopping cart. We do not need an AI for that.
No, of course not. We know the exact math. It is a flat percentage. You write a traditional program, data plus program equals output.
But what happens when you want a computer to look at a million photographs and identify which ones contain a cat?
Right, a human programmer cannot write rule-based code for a cat. You can't just say, if pixel 400 is orange and pixel 401 is black, then it is a cat. Because the lighting changes, the angle changes. The cat might be hiding behind a couch, or it might be a hairless cat.
The mathematical functional relationship between raw image pixels and the concept of cat is vastly too complex for a human brain to write as a standard rule. This is where we need algorithms to approximate that function for us.
Right, algorithms like neural networks, boosting, decision trees, or support vector machines.
Exactly.
Let's pause on those terms for a second, because that is where the buzzwords really start flying in those vendor pitch meetings. When a startup throws around a term like support vector machine or a decision tree, what are they actually talking about?
Strip away all the jargon, and they are just different mathematical strategies for sorting data. That's it. A decision tree is essentially just a massive high-speed game of 20 questions. The algorithm asks a series of yes or no questions to categorize data.
Okay, what about a support vector machine?
A support vector machine, or SVM, is basically drawing a boundary line. Imagine you scatter a bunch of red and blue marbles on a table. An SVM is an algorithm that tries to draw the straightest possible line to separate the red marbles from the blue ones.
And a neural network?
A neural network is just a web of simple mathematical nodes that pass signals to each other, vaguely inspired by the human brain, adjusting their connections until they recognize a pattern. They're all just different ways of finding the recipe when you only have the ingredients and the picture of the cake.
Now, the Lancaster source makes a critical point about scale here. These algorithms only become necessary and powerful when we're dealing with high-dimensional data.
High-dimensional data is the trigger for needing machine learning. Let's look at a modern piece of heavy machinery, like a commercial jet engine.
Okay.
That engine might have thousands of microscopic sensors recording temperature, pressure, vibration, and fuel flow, all generating new readings hundreds of times a second. Every single sensor is a dimension of data.
And a human being cannot look at a spreadsheet with a million columns of chaotic sensor data and spot the incredibly subtle pattern that indicates the engine is going to fail in exactly 3 weeks.
Exactly. It's impossible. But a machine learning algorithm, given enough historical data of engines running normally and engines failing, can find that hidden structure. It reduces those thousands of dimensions down to a single output, healthy or failing.
When you explain it like that, the technology genuinely sounds revolutionary. I mean, it solves problems we literally could not solve 10 years ago.
It is revolutionary.
But that immense power brings us right back to the fever. Because the tech is so powerful in specific applications, the expectations have completely detached from reality. The Lancaster presentation references the 2016 Gartner Hype Cycle for Emerging Technologies, which perfectly maps this phenomenon.
The Gartner Hype Cycle is an essential framework for any executive. It traces the journey of a new technology. It starts with an innovation trigger, some early proof of concept stories. Then the media gets hold of it, and it rockets up a steep curve to what Gartner calls the peak of inflated expectations.
Which is the danger zone.
It is. Everyone thinks the technology is a magic wand. Eventually, reality sets in, projects fail, and the tech crashes down into the trough of disillusionment.
And only after that crash does it slowly climb the slope of enlightenment, where people figure out its actual practical uses, finally reaching a plateau of productivity.
Right. And in 2016, and arguably continuing today in different forms, machine learning was sitting at the absolute pinnacle of that peak of inflated expectations.
The Bain & Company white paper put some staggering numbers to this fever. They tracked corporate earnings calls, and in a single recent quarter, nearly 20% of all corporate earnings calls included some mention of artificial intelligence or machine learning.
1 in 5 public companies felt compelled to tell their shareholders that they were doing AI. That proves the fever is institutional. Executives are adopting the technology not because it fits their operational model, but because they're terrified of looking outdated to Wall Street.
With all this institutional pressure, the natural instinct is to apply machine learning to absolutely everything, every department, every process, every spreadsheet. But our sources explicitly warn against this. They put up giant flashing red "Do Not Enter" signs.
Yes, they do.
So let's navigate those boundaries. Quimatics, paired with the engineering rules from Google, outlines 4 specific scenarios where using machine learning is a terrible, expensive mistake.
The best place to start is with Google's rule number 1. Martin Zinkovich from Google is one of the top ML engineers on the planet, and his very first rule for machine learning engineering is, don't be afraid to launch a product without machine learning.
Coming from Google, an AI pioneer, that is a stunning piece of advice. The primary rule of AI is, you probably don't need this yet. That leads directly into the first "Do Not Enter" sign from Quimatics, which they call the cold start problem. Or, more simply, no data.
Machine learning is entirely dependent on historical data to find patterns. It is an engine that runs exclusively on the past. Without a massive repository of historical data, there is no machine learning, period.
Let me play devil's advocate and push back on that, because I can hear an ambitious product manager arguing this point right now.
Okay, let's hear it.
Let's say I am launching a brand new, totally disruptive product line. I want to use ML to predict which of my current customers are most likely to buy it. Now, I have millions of rows of data on my customers' past behavior. Why can't the AI just figure out who will like the new product?
Because the AI has never seen the new product before. It doesn't know what the cake looks like. It is a completely cold start. A machine learning model cannot generate a recommendation out of thin air. It requires a baseline correlation.
But the ambitious product manager might say, well, we can just use proxy data. We will map the sales data from a similar product we launched 3 years ago and feed that into the model.
It sounds reasonable. If you're launching a new running shoe, you just train the AI on the sales data from your last running shoe.
Right. Why wouldn't that work?
It introduces massive vulnerability. You are training the algorithm to optimize for the past product, not the new one. If the new shoe has a slightly different price point or appeals to a slightly younger demographic, the algorithm won't know that. It will confidently spit out recommendations based on an outdated reality.
Ah, yeah.
In a true cold start scenario where you are launching something radically new with unprecedented market dynamics, ML cannot help you until you generate enough actual real-world baseline data from the new launch.
Okay, so sign 1 is no data. Sign 2 touches on the fundamental mathematical nature of how these algorithms operate. Do not use machine learning if your business use case has a zero tolerance for mistakes and you do not have a human supervisor in the light.
This requires a shift in how we think about computers. We are used to computers being deterministic. A calculator always says 2 plus 2 is 4. But almost all machine learning systems operate probabilistically.
Right.
When an image recognition model analyzes a photo, it does not output a definitive, this is a cat. It outputs, there is a 94.7% probability that this pixel arrangement represents a cat.
Which means it is guessing. It's a highly educated, mathematically complex guess, but it's still fundamentally a guess.
Exactly. Even the absolute best, most advanced ML systems in the world, the ones boasting 95% or 98% accuracy on their marketing brochures, are mathematically guaranteed to fail 2% to 5% of the time. It is baked into the nature of the technology.
So the executive question is not will it fail? The question is, what is the cost of a failure?
Precisely. Let's look at a low-stakes environment first. If I log into Netflix and their incredibly expensive ML recommendation engine suggests a terrible movie, what is the actual damage to the business?
The damage is practically zero. You watch 10 minutes, you get bored, you turn it off, and you pick something else.
Or if Amazon recommends a blender you don't want, you just don't click on it. The cost of that error is negligible. But the upside of those probabilistic guesses is astronomical. The Quimatics paper notes that 25% of Amazon's entire revenue comes from these probability-based recommendations. So in a low-stakes environment, occasional errors are a totally acceptable cost of doing business because the massive scale of the upside vastly outweighs the minor annoyance of a bad guess.
Let me play devil's advocate here again, though. Let's look at a high-stakes environment like medicine. We're seeing hospitals implement ML systems to read patient x-rays and identify early-stage tumors.
Right.
Now, a mistake there is fatal. It is literally life and death.
Yeah.
But aren't machines inherently less prone to error than tired, biased humans? Why wouldn't I want an AI doctor over a human radiologist who has been awake for 20 hours?
Because the machine lacks contextual common sense, and its failures can be catastrophic in ways a human failure wouldn't be. A tired doctor might miss a subtle shadow. A machine learning model, if encountering an artifact on the X-ray it hasn't seen in its training data, might confidently diagnose a completely impossible condition.
Oh, I see.
This is why medicine implements this technology purely as an assistive tool. They use ML to scan thousands of images and flag potential issues, but a highly trained human professional, a supervisor, always remains in absolute control of the final diagnosis.
The ML provides a probabilistic recommendation, but the doctor checks that recommendation against their own expertise, other blood tests, the patient's history.
Exactly. If your business use case allows zero tolerance for error and you cannot afford to pay a human professional to constantly check the machine's math, you must not use machine learning.
That makes a lot of sense. And that perfectly transitions us to the third do not enter sign, which moves entirely away from the math and right into human psychology.
Right.
Quimatics identifies this as cultural resistance.
This is a big one.
You can build the most mathematically perfect, highly accurate ML model in the world. But if your employees are not culturally prepared to interact with it, it becomes shelfware 2.0. Just an incredibly expensive piece of software gathering digital dust.
The most successful machine learning applications in business-to-business environments are hybrid systems. Humans using AI as a support tool. But introducing algorithms into the workplace requires a fundamental shift in daily routines, and humans hate changing their routines.
We really do.
There is an entire field of study emerging around this called algorithmic management. It deals specifically with the friction of the human-machine interface in the workplace.
Paint a picture of what that friction actually looks like on the ground.
Imagine a veteran sales representative who has been working the same territory for 20 years. They know their clients. They have a gut instinct for when a deal is going to close.
They know the rhythm of the business.
Exactly. Now, management rolls out a new ML-led scoring tool. The algorithm analyzes thousands of variables and tells the sales rep, stop calling client A and spend all your time on client B.
Right.
To the sales rep, this feels completely counterintuitive. If there is no mechanism for the rep to understand why the machine is making that recommendation, or no control mechanism for the rep to reject it and say, no, the machine is missing context, the rep will simply ignore the software.
A system is only as good as its users. If your culture rejects the implant, the project fails. Not because the math was wrong, but because management failed to account for human pride and intuition.
Precisely.
Which brings us to the fourth and perhaps most common do not enter sign. Do not use machine learning if a simple rule-based solution works perfectly fine.
This is a definition of using a sledgehammer to crack a nut. Quirematics uses a great, simple example. Let's say your business objective is to identify lapsed customers so you can send them a discount code. Your internal rule is, if a customer has not bought anything in more than 90 days, flag their account. You do not need a neural network for that. A human sets the rule, a basic Excel spreadsheet executes it, and you achieve your business goal.
This aligns perfectly with Google's engineering wisdom. Martin Zinkovich's rule number 3 states, choose machine learning over a complex heuristic. The key word there is complex. He advises you to keep simple heuristics. But for the non-engineers listening, what exactly does he mean by a heuristic?
A heuristic is just a rule of thumb, a mental shortcut, or a simple hard-coded rule in a software program. If X happens, do Y. Zinkovich points out that a simple heuristic might get you 50% of the way to your goal immediately with almost zero engineering cost.
Right.
Why would you waste 6 months of expensive engineering time and massive amounts of computing power building and training an ML model when a basic, simple rule solves the immediate business need today?
So when do you actually make the switch?
You only switch to machine learning when those simple heuristics become so complex, so tangled, and so difficult to maintain that the system starts collapsing.
Oh, like a spider web of rules.
Exactly. If your rule becomes, if the customer hasn't bought in 90 days, and they live in the zip code, indeed they previously bought the specific item during a Tuesday rainstorm, suddenly your human-written rules are unmanageable. That is when you need an algorithm to find the pattern.
Here's where it gets really interesting. This is incredibly clarifying. We have established the boundaries. We know to avoid the cold start. We understand the probabilistic stakes. We know we need human buy-in, and we know our simple rules have maxed out.
We've done the groundwork.
Exactly. We have navigated the minefield and decided we absolutely definitively need machine learning. But how do we build it? How do we avoid catching AI fever and blowing millions of dollars on a failed experiment?
This is where we shift from theory into rigorous execution. The Bain & Company white paper provides a 5-step playbook for building real AI. They treat it as a strict, disciplined process rather than a magic wand.
And we are going to heavily augment Bain's high-level strategy with the deeply granular engineering rules from Google. Because bridging the gap between the executive suite and the engineering floor is where these projects succeed or fail.
Let's do it.
Step 1's a playbook. Set the business context. Bain says you never, ever start by picking an algorithm. You start by choosing a quantifiable business objective and establishing a clear baseline that you want to beat.
This sounds obvious, but it is where most projects fail on day one. Bringing in the Google perspective, Zinkovich's rules 12 and 13 are vital here.
What are they?
Rule 12 says, don't overthink which objective you choose to directly optimize. And Rule 13 is the real warning. Choose a simple, observable, and attributable metric for your first objective.
Explain why that is a trap. If I am the CEO, my objective is make the users love our app more. Why can't I tell the AI to optimize for user happiness?
Because an algorithm cannot read an emotion. How do you quantify happiness in a mathematical weight? You cannot. Google strongly advises avoiding indirect effects initially.
Oh, I see.
Executives often want to model complex, long-term behaviors like, did the user visit the site again the next day? Or did their long-term brand loyalty increase? Those are fantastic metrics for a marketing team doing long-term A/B testing, but they are terrible metrics for training your very first ML model.
So what should that CEO tell the engineering team to optimize for?
Google says to measure direct, instantly observable actions? Was the specific link the AI recommended actually clicked? Was the specific file downloaded? Was the email marked as spam? Yes or no?
Keep it binary.
Exactly. If you try to build a model that optimizes everything, clicks, time on site, long-term retention, and brand loyalty, the math becomes muddy and you end up optimizing nothing. You have to translate your grand, abstract business objective into a highly specific, immediately measurable machine learning objective.
Okay, once you have that single simple metric, you move to step 2.
Hmm.
Engineer the data. Bain makes a profound point here, one that goes against a lot of modern tech marketing. They state that the pros know better data almost always beats a better algorithm.
It's the truth.
Companies get obsessed with buying the latest, fanciest third-party data sets from data brokers. But Bain emphasizes that first-party data, the data you naturally generate from your own direct interactions with your own customers, is usually far superior, cleaner, and more predictive.
And this is where the Google engineering rules give us some stark, terrifying warnings about data handling. Let's look at Google's rule number 6. Be careful about dropped data when copying pipelines. Zinkovich refers to the cause of this as cargo cult programming.
Wait, cargo cult programming? That sounds like an oxymoron. What does a cargo cult have to do with Silicon Valley software engineering?
It is a brilliant term derived from anthropology. During World War II, the military built air bases on remote islands in the Pacific, bringing in planes full of cargo and supplies.
Okay.
After the war, the military left. The indigenous people on some islands built mock airstrips and wooden airplanes, mimicking the behavior of the soldiers, hoping the cargo planes would return. They replicated the form but didn't understand the underlying mechanics. In software engineering, cargo cult programming describes a situation where a junior engineer copies a piece of code or a data pipeline from an older, successful project without truly understanding how it works, simply because it worked before.
Ah, I see the connection now. So how does that destroy a machine learning project?
Zinkovich points out that when you blindly copy an old data pipeline, you might inherit old rules that accidentally drop the exact data your new model desperately needs.
Like what?
He gives a great example regarding visibility. Let's say your old traditional software pipeline was designed to save server space, so it only logged data for items that a user actually saw on their screen. Everything else was deleted.
Makes sense for saving space.
Right. But now you are building a new machine learning model to figure out why users aren't engaging with certain items. If your copied pipeline automatically drops all the data for items the user never saw, your new model has no negative examples to learn from.
Oh, it's flying blind.
Exactly. And the engineers won't understand why because they just copied a pipeline they assumed was safe.
That is a terrifying hidden trap. And there's another crucial data rule, Google's Rule 11. Give feature columns owners and documentation. What is a feature column and why does it need an owner?
A feature column is basically a specific type of data you are feeding the model. Age, zip code, time of day, last purchase date, those are all features. In a massive enterprise system, you might have hundreds or thousands of these features feeding into the algorithm.
Right.
Zinkovich warns that if the specific human engineer who created and understands a specific data feature leaves the company and they didn't write down exactly how that feature is calculated, your entire ML system is suddenly at risk.
Because nobody knows what that data point actually means anymore.
Exactly. You literally have parts of your corporate brain that nobody in the building understands. If that data feed breaks, nobody knows how to fix it.
So we have a simple metric, and we have carefully engineered, documented, first-party data. Now we reached step 3, develop the model. Bain stresses that this must be done in agile sprints. We're talking 2 to 4 week cycles.
Right.
You do not lock your data science team in a basement for a year to build a super brain in secret. You build something small, and you immediately compare it to the baseline you established in step 1.
This is where Google's Rule 4 is absolute law. Keep the first model simple and get the infrastructure right. Zinkovich stresses that the very first model you deploy provides the biggest marginal boost to your product.
Because anything is better than nothing at that point.
Exactly. Going from 0 ML to a basic ML model gives you a massive jump in efficiency. Going from a basic model to a highly complex, deep learning model only gives you incremental gains. Therefore, the first model absolutely does not need to be fancy. In fact, he argues that the majority of the work in step 3 isn't the machine learning at all. It is building the plumbing.
The plumbing.
The infrastructure surrounding the brain. How do you reliably get millions of data examples into the algorithm every hour? How do you mathematically define what good and bad outcomes mean for the system? And most importantly, how do you actually integrate the output of the algorithm back into your live user-facing application without crashing it?
Right, the connections.
That plumbing is far more important than the algorithm itself initially.
Zinkovich also adds Rule 14 here. Starting with an interpretable model makes debugging easier. This feels like a direct pushback against the hype of massive, opaque black box neural networks.
It is a massive pushback. He advocates starting with something like linear regression, logistic regression, or Poisson regression.
Okay, let's translate that for the executive listener. If my engineering team comes to me and says they want to use Poisson regression instead of a deep neural network, why should I be happy about that?
You should be thrilled because you can read the math. Poisson regression is a statistical model specifically used for predicting counts, like predicting exactly how many times a specific user will click an ad in a given week.
Okay.
Because it is a traditional statistical model motivated by probability, it is interpretable. If the model suddenly predicts a user will click an ad 10,000 times, a human engineer can open up the model, look at the math, and say, the weighting on the time of day variable is broken. They can debug it.
Whereas a neural network is just a black box.
Exactly. If you start with a massive, uninterpretable black box neural network and it starts behaving erratically, the internal weights are hidden across millions of microscopic nodes. Debugging it is a nightmare. You establish the plumbing first with a simple, transparent, interpretable model.
That makes perfect sense. Ask your team if they can read the math. If they can't, don't sign off on it for version 1. That brings us to step 4. Deploy the model. Bain says you have to test with real users and identify the needed infrastructure changes before you write those 7-figure checks to vendor platforms. You need to know how the system reacts in the wild.
Deployment is where things get genuinely terrifying from an engineering perspective and where executives really need to ask hard questions. Zinkovich lays out several critical rules for this phase. Let's look at Rule 8. Know the freshness requirements of your system.
Freshness requirements, meaning how quickly does the data rot?
Exactly. You need to know exactly how quickly your model's performance decays if it is not fed new data. Does a model that is 1 day old lose 10% of its revenue-generating power? What if it is a week old?
I imagine it varies wildly by industry.
It does. If your business is serving online advertisements, you probably need to update the model daily or even hourly because new ad campaigns arrive every single day and user trends shift overnight. If you are predicting long-term mortgage defaults, maybe you only need to update the model once a month. As an executive, if your team cannot answer the question, what is our freshness requirement, you should not deploy the model.
Zinkovich notes that for Google Play Search, if the ML model is not updated, it starts negatively impacting app installation revenue in under a month. So freshness is critical. Then he gives Rule 9. Detect problems before exporting models.
This is basic safety hygiene, but it is often skipped in the rush to launch. If a model acts up before it is exported to the live production server, it is just an internal training issue. Nobody gets hurt. But if you export a broken, erratic model, suddenly millions of your actual users are having a terrible experience. You have to do automated sanity checks right before export.
He mentions checking the area under the ROC curve. Again, for the non-engineer, what is the executive summary of an ROC curve?
ROC stands for Receiver Operating Characteristic. Without getting into the heavy math, an ROC curve is basically a chart that measures how well your model balances true positives against false positives. It measures its ability to distinguish between the signal and the noise. If the area under that curve suddenly drops during a training run, it means your model has gone blind. You want an automated system that checks that curve, and if it drops, it refuses to export the model to the live server.
But the absolute scariest warning in the entire Google playbook is rule number 10. Watch for silent failures.
Silent failures are a unique, insidious nightmare specific to machine learning. In traditional rule-based software, if a critical database table stops updating, the program usually crashes. You get a massive red error code on your dashboard. The system stops, and you know immediately that something is broken.
But a machine learning system is fundamentally designed to adapt to whatever data it is given.
So it doesn't crash, it just improvises.
That sounds dangerous.
It is. Let's use a hypothetical scenario. Imagine you run a massive e-commerce site and you deploy an AI to optimize the prices of your shoes in real time based on competitor pricing. Now, suppose the database tracking your competitors' prices freezes due to a server glitch. It stops updating, The AI won't crash. It won't throw an error code. It will simply look at the frozen data, assume competitor prices have magically stabilized, quietly adjust its internal weights, and start pricing your shoes based on 6-month-old market data.
Wow.
You are losing millions of dollars in margin, but your executive dashboard says the AI is running perfectly smoothly. That is a silent failure.
Zinkovich gives a mind-blowing real-world example of this from Google Play. They discovered a data table feeding their app recommendation model that had been stale, completely frozen for 6 solid months. Nobody noticed because the system never crashed. It just adapted to the stale data. When an engineer finally found it and simply refreshed that one single data table, the overall app install rate for Google Play jumped by 2%.
That is a staggering amount of revenue found just by fixing a frozen table. It proves that basic data hygiene and building alarms to detect silent failures is often vastly more powerful than inventing a fancy new algorithm.
Finally, we reach Bain's step 5, ensure adoption. This loops back to the cultural resistance we discussed earlier. You have to propagate the vision through what Bain calls the sponsorship spine.
The sponsorship spine means you need alignment at every vertebral level of the company. You need the top-level executives who are sponsoring and funding the change to understand the limits of the tech. You need the middle managers to understand how it changes their KPIs.
And crucially, you need the frontline workers, the people who actually have to implement and use the recommendations on their screens to trust the system.
If the spine is broken at any level, the project becomes shelfware.
So we have the theory, we have the boundaries, we have the 5-step playbook and the granular Google engineering rules. But it's easy to talk about this in the abstract. How does this actually play out when the stakes are hundreds of millions of dollars? Our sources give us 3 incredibly detailed case studies. Let's look at real-world triumphs and massive scale.
The first case study from Bain & Company involves a massive telecom price war. A large, established mobile carrier was suddenly facing an existential threat. A major competitor slashed prices drastically, initiating a brutal price war, and customer churn, the rate at which people were canceling their contracts, spiked to terrifying levels.
It was absolute panic stations. Initially, the carrier strategy team thought they had 10 weeks to formulate a response to this threat. But then a second major competitor joined the price war, and suddenly that 10-week window shrank to just 5 weeks.
Now, the instinct here would be the ultimate AI fever response, right? Panic, call a massive vendor, buy an incomprehensible deep neural network, and hope it magically identifies which customers are about to leave and offers them a discount.
But they didn't do that.
No, they followed the playbook. They implemented week-by-week agile release cycles. They didn't start with a multi-million-dollar vendor. They started with open-source tools and simple, interpretable classification models.
They focused on getting slightly better targeting models and slightly smarter retention offers rolled out every single week. They tested them in waves with control groups, and then they did something incredibly smart with their data engineering. They didn't just use standard billing records.
Right, they went deeper into their first-party data. They utilized a technique called deep packet inspection.
Break that down for us. What is deep packet inspection?
When you send data over a mobile network, like an email or a video, it is broken down into little digital envelopes called packets. Normally, a telecom only looks at the outside of the envelope. Where is it going and how big is it?
Like reading the address on a letter.
Exactly. Deep packet inspection means they actually look inside the envelope. They gather highly granular real-time data on user behavior directly from the network traffic itself. Are they streaming high-def video? Are they constantly dropping calls in a specific zip code?
That's incredibly specific data.
It is. They took this rich behavioral first-party data and fed it into their increasingly sophisticated but still transparent models.
And what was the result of this agile, transparent approach? By combining this highly accurate targeting with smart, personalized pricing tactics, they reduced customer churn by 60%. They brought the cancellation rate entirely back down to historic pre-price war levels.
Which is incredible.
And crucially, they did this while building immense trust with their human marketing team. Because they deliberately avoided using opaque deep learning models initially, the human marketers could look at the output and understand exactly why the system was recommending a specific discount to a specific user. The spine of adoption was strong.
The second Bain case study looks at a completely different industry with a completely different human problem: consumer goods returns. A major consumer products firm was losing an absolute fortune on excessive product returns.
Why?
The reason was entirely human. They had tens of thousands of field reps, the people actually driving the delivery routes and stocking the shelves at local stores, who were constantly padding their recommended orders.
The company had a basic demand forecast model, but it was a blunt instrument. It made broad predictions for the whole country, but it was terrible at predicting what a specific corner store on a specific street actually needed on a Tuesday.
Right. So the field reps, knowing the corporate model was flawed locally, just ordered extra inventory to be safe. They didn't want to run out of stock and lose a commission.
Makes total sense from their perspective.
That human behavior led to massive overstocking and eventual waste when products expired or didn't sell and were returned to the warehouse.
The company realized that just buying a better AI and forcing a top-down algorithmic mandate on tens of thousands of independent-minded field reps would be a cultural disaster. The reps would just ignore it.
So they went to work on the data first. They built a massive, clean database using years of historical order and return histories. Then they used open source libraries to build a new, highly granular machine learning forecast model that could actually predict local street-level demand.
But the genius was in step 5, adoption. They didn't just email the reps a new spreadsheet and say, follow the AI. They developed an entirely new interactive interface for the field reps.
They allowed the reps to consume the AI forecast, test it, adjust it, and slowly build trust in the machine's accuracy. It was a true hybrid system.
By addressing the human element, by actively engaging in algorithmic management, they successfully deployed a system that dramatically reduced returns and generated an expected 9-figure annual payback.
That is hundreds of millions of dollars saved.
Not by buying the best algorithm, but by building the best user interface for the humans using the algorithm.
In both of those Bain case studies, you notice a pattern. They are holding off on complex, deep learning AI until they absolutely need it. They are letting the specific business problem and the human psychology of their workers dictate the technology.
Which brings us to our final and most technically complex case study, next-generation networks, from Daniel King's presentation at Lancaster University.
This takes us entirely out of corporate strategy and into the absolute bleeding edge of global physical infrastructure. We are talking about how telecommunications networks physically route the internet around the world using SDN software-defined networking and NFV network functions virtualization.
The stakes here are the literal backbone of the modern economy. Customers demand rapid delivery of new services, massive bandwidth for streaming and cloud computing, and highly sophisticated service-level agreements guaranteeing uptime.
Meanwhile, network providers need to drive up income while reducing the massive operational costs of running these networks.
The old traditional way of solving network congestion was primitive. They called it throwing resources at the problem. If a network got slow, you just build a fat pipe.
Right. It is like trying to solve rush hour traffic in a city by just building a 50-lane highway everywhere. Yes, it solves the traffic jam, but it costs a fortune to build. It takes up massive amounts of real estate. And for 90% of the day, 45 of those lanes are completely empty and wasted.
As global data usage explodes, building endless 50-lane digital highways is too expensive and totally impractical.
So inevitably, these digital links reach critical utilization. They get jammed. And it is incredibly hard to predict which links will fail or where a sudden surge of new customers will cause unforeseen congestion. Networks need complex, real-time path computation.
They have to model the entire network across multiple layers, balancing completely conflicting constraints. They have to minimize cost, minimize delay, and maximize bandwidth, all simultaneously in milliseconds.
King's presentation points out that the existing computation techniques, the traditional algorithms, are hitting a brick wall. A standard protocol used for decades is called CSPF, or Constrained Shortest Path First.
Explain CSPF simply.
CSPF is like a basic GPS in your car. It is perfectly fine for computing a single optimal path from point A to point B. But if 3 different roads are closed and there is a sudden traffic jam on the detour, and you also need to stop for gas, the basic GPS struggles to compute all those conflicting constraints in real time. CSPF cannot handle multi-constraint network problems efficiently.
So then engineers tried using linear programming.
Right. Linear programming is a mathematical method that can optimize a whole network. But to use the traffic analogy again, linear programming is like hiring a city planner to draw a perfect map of the city. It takes them a week to calculate the absolute perfect traffic flow. By the time they finish the math, the traffic jam is over and a new one has started somewhere else. It is far too slow to develop and compute, and it is far too inflexible to handle rapidly changing demands or new network topologies on the fly.
These deterministic algorithms, which produce the exact same solution every time and are tuned to older, simpler technologies, are simply too slow for the modern internet. This is where machine learning is stepping in to save the day.
Non-heuristic ML processes can assess a vastly wider variety of real-time data to derive routing solutions dynamically. It is like a dynamic traffic control system that can instantly open and close lanes or reroute cars globally based on where the traffic actually is right now.
The industry is getting so serious about this that they are forming massive working groups, like the IETF IDNet, the Intelligence Defined Network. They are trying to build an entirely new global architecture to apply ML to network control directly.
But what fascinates me is that even at this absolute bleeding edge of global technology, the exact same fundamental rules we discussed earlier still apply. King points out that before they can even use the AI, they have a massive data problem.
Yes. He notes that standardized, labeled datasets for network traffic are incredibly scarce. The standard data sources that networks have used for years, like NetFlow, were designed for basic billing and monitoring. They were never originally designed to feed a machine learning algorithm.
So before these brilliant engineers can even unleash the fancy open source ML frameworks from Google, Facebook, or Amazon, they have to go back to step 2. They have to completely rethink and rebuild their foundational data structures.
And he highlights a massive skills gap. You can download Google's TensorFlow algorithm for free right now, but the machine does not build itself. It still requires immense, highly paid human skill and experience to build deep neural network architectures, and crucially, to find the good settings for the hyperparameters.
Hyperparameters are a great concept to end on. If the algorithm is an engine, the hyperparameters are the master dials and knobs on the outside of the engine that the human engineer has to tune before the machine even starts learning.
How fast should it learn? How many layers should it have?
Exactly. If a human doesn't tune those dials correctly based on experience and intuition, the AI will fail. The human is still the bottleneck.
If we pull all the way back and look at the bigger picture, these 3 examples, the telecom carrier, the consumer goods company, and the engineers building the next generation of the internet, all prove the core thesis of our deep dive today. Do not start with the most complex technology.
The telecom company avoided opaque deep learning, specifically to build trust with their human marketing team. The consumer goods company realized the math didn't matter at all if they didn't build an interface the field reps would actually want to use.
And the networking engineers at the absolute frontier of technology are realizing their basic data plumbing isn't ready for ML, and they have to go back to the absolute basics of data hygiene.
The cure for AI fever isn't to ignore AI, and it certainly isn't to be afraid of it. The cure is to respect the rigorous process over the hyped tool.
True innovation does not come from downloading an algorithm or hiring a startup with a WeWork office. It comes from deeply understanding your specific business context, ruthlessly cleaning your first-party data, starting with simple, transparent heuristics, and carefully managing the human adoption curve.
We have covered so much ground today, from the WeWork hype to the Google engineering trenches to the global data networks. It all comes down to focusing on the fundamentals. But before we wrap up, this research raises a deeply important, almost philosophical question that builds directly on Quimatics's concept of algorithmic management in our discussion about medical supervisors.
I love where this is going. What is the question we need to be asking as we scale this up?
Think about this. We currently implement AI in high-stakes fields like medicine with the strict absolute rule that a human supervisor must always remain in control to check the AI's probability-based math. The doctor's in charge.
Right.
But as these ML models become smoother, faster, and more deeply integrated into every single interface we use daily, the friction disappears.
The machine just gets better and better at guessing what we want.
Exactly. And human beings are inherently wired to conserve cognitive energy. If an AI gives you a recommendation that is right 98% of the time, eventually you stop checking the math on the 2% where it might be wrong. You just click approve.
Because it's easier.
Right. So the question is, as we defer to these systems to save time and cognitive load, are we really supervising the AI anymore? Or is the algorithm slowly, quietly training us to stop questioning the machine entirely?
That is a chilling thought. It is the GPS effect, right? Before smartphones, people knew how to navigate their cities. Now, we blindly follow the blue line on the map, even if it tells us to drive into a lake. Our innate sense of direction has atrophied because we deferred to the algorithm.
Precisely. Now map that GPS effect onto a corporate executive or a medical professional. If a manager defers to an AI for every supply chain decision for 5 years, does their innate business instinct atrophy? If a doctor clicks approve on an AI diagnosis 1,000 times, do they lose their diagnostic edge?
Who is managing who in that scenario?
Exactly. The risk isn't a sci-fi robot takeover. The risk is a slow, comfortable erosion of human critical thinking.
Are we the supervisors, or are we the ones being conditioned by the convenience of the algorithm? That is exactly the kind of question we need to be asking as this technology scales into every corner of our professional lives. Take a closer look at the algorithms operating in your own daily life this week. Question the recommendations, check the math, and remember to trust the process, not just the hype. Keep learning, and we will catch you next time.